Hello students, today I welcome you in the session of physics, and in physics today we will study about the gravitation. This is your chapter number 12. So in this chapter we will know about what are planets and satellites. This come to the first, we will take first Kepler's law of planetary motion. As you can see, this is the topic we have to study. Our solar system consists of a sun, which is stationary at the center of the universe, and 8 planets which revolve around the sun in separate orbits. I hope you are familiar with the planets. There are 8 planets which are revolve around the sun in separate orbits. The name of the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Now Pluto is removed from the planets because it is a dwarf planet. So the planet Mercury is closest to the sun and the Pluto is the farthest. There are certain celestial bodies. So what are the celestial bodies? The bodies which are hypothetical. Clear? They are known as celestial bodies which revolve around the planets. These are called satellites. For example, Moon revolves around the Earth and Moon is a satellite of the Earth. As we all know that Moon is a natural satellite of the Earth. Similarly, Mars has 2 satellites, Jupiter has 16 satellites, Saturn has 19 satellites, and so on. So we will now discuss about Kepler's law. Kepler found important regularities in the motion of planets. Clear? These regularities are known as Kepler's law. They give 3 laws of, these are known as 3 laws of Kepler, as you can see here. So the first law is known as the law of orbit. What does it say? All the planets move around the sun in elliptical orbit having sun at one focus of the orbit. As you can see, this is the first law that is known as law of orbit. And according to this law, all planets move around the sun. This is, as you can see in your figure number here 1. Clear? So in this figure, it is given that all the planets move around the sun in elliptical orbit. Not in circular orbit, but it is in elliptical orbit having sun at one focus of the orbit, and sun is at the focus of the orbit. Clear? This is the first law. As you can see in the figure number 1, here the sun is at the focus of one planet is moving from position A to B and the other one is from C to D. The second one is the law of area. So the law of area says that a line joining any planet to the sun sweeps out equal area in equal time. That is, the aerial velocity of the planet remains constant. So as you can see here, a line joining any planet means if you join a line, that is we have joined the A and B to the sun and also C to D to the sun. So they both are sweeps out equal area in equal time. This is the aerial velocity of the planet, that is the aerial velocity of the planet around the sun remains constant. Now what is the aerial velocity? Velocity which cover a certain area. Clear? That is known as aerial velocity. When the planet is nearest the sun, then its velocity is maximum. What is written here? When the planet is nearest to the sun, in that case the velocity is maximum. When it is farthest from the sun, in that case the velocity is minimum. Clear? Now we will move to, here it is written figure 10, but it is wrong. Actually this is figure number 1. So in figure 1, if a planet, here it is, mark it correction here, this is figure 1. If a planet move from A to B, just see the figure number 1. Suppose a planet is moved from A to B in a given time interval. Clear? And from C to D in the same time interval. Then according to the law of area, the area is your ASB and CSD will be equal. Clear? Because they sweeps out equal area in equal time. This is the Kepler's second law. Now we will move to law of period, which is Kepler's third law. You can see here, this is the law of period. So what does it say? The square of the period of revolution of any planet around the sun is directly proportional to the cube of its mean distance from the sun. According to the third law of Kepler, which is known as law of period, the square of the period means the time taken by a planet to revolve around the sun is known as time period. So the period of revolution of any planet around the sun is directly proportional to the cube of its mean distance from the sun. That is, you can say like this: if the period of a planet around the sun, we suppose the period of the planet around the sun is t, and the mean radius of its orbit is how much? R. Then t is square is proportional to r cube. That is the thing is given in the third law. Clear? So t square is proportional to means the time period, the square of the time period is proportional to the cube of distance. If we remove the sign of proportionality, so what we get? We get t square equals to k times of r cube, where k is the constant. I hope it is clear. The larger the distance of the planet from the sun, larger will be its period of revolution around the sun. This is the important thing written here. The larger the distance of a planet from the sun, larger will be its period of revolution around the sun. Clear? Means as long as the distance of planet from the sun, its period of revolution is also greater. Now we will prove the gravitation derivation of Kepler's law. This is optional, but I will tell you how you can prove it in later. We will move to Kepler's first law. As you show, as shown in figure 2, here you can see this is the figure number 2, this one. The planet whose mass is small m, clear, is acted upon by a gravitation force F directed towards the sun. Here you can see that at center point there is a sun, this one, and from the sun the distance to the planet is taken as vector r. A force is experienced by a planet due to the sun, clear, which is known as acted by a gravitation force. Force F directed toward the sun, and the line of action of that force is directed toward the sun. As sun is attracting the planet which is moving around it. Since force is a central force, the angular momentum J of the planet with respect to the center of force is constant. You know, which is F is a central force. And one thing I would like to tell you here, this force also provides the necessary centripetal force to the planet. I hope you know what is centripetal force and centrifugal forces. So here F is a central force, the angular momentum, that is J, you know the linear momentum and angular momentum. So here the angular momentum of the planet, because here the planet is moving at a particular direction and forming an angle. That's why we are taking here angular momentum. And if a particle is traveling in a rectilinear path or a horizontal direction, a linear direction, then we take their linear momentum. So here J is what? J is a planet with respect to it is an angular momentum with respect to the center of force is constant in magnitude and direction. That is, you can write like this. In linear momentum, you take P is equals to mv, where m is the mass, v is the velocity. But right now here in angular momentum, we take vector r into P, where P is your momentum, r is the distance of the planet from the sun. So vector J is equals to vector r cross vector P. In place of P, we write here you can see P is equals to how much? mv. So this multiplication or this cross product is equals to constant, where r is the radius vector of the planet with respect to the sun, and v vector is its velocity. Since vector r and vector v are always perpendicular to the angular momentum, or you can say vector j, so the orbit of the planet always lie in a plane perpendicular to j. This is at least a partial proof of Kepler's first law. Now we will move to Kepler's second law. What is Kepler's second law? Here you can see this is the Kepler's second law. So let us consider the geometric argument here as shown in the figure number 3. You can see this is the Kepler's figure of Kepler's second law. So let us consider the geometric argument as shown in figure 3 as the planet move from P to P dash. Suppose at the initial point the planet is at P, and in a small time interval or a very small time interval, that is delta t, it changes its position from P to P dash. Clear? The radius vector, which is your vector r, sweeps out an area. When the planet moves from P to P dash, it sweeps out an area which is known as delta vector A. Here we show the area covered by the planet by the shaded portion. So how we can evaluate this area? As we all know, it is forming a triangle. You can see here in the figure number 3, I will show you. Here you can see this is forming a triangle. Clear? So what is the delta r vector? Is nothing but a height, and the base is your horizontal direction. So it is your vector r. So as we all know, the area of a triangle can be found out with the half base into height. So here you can see the base is vector r. Clear? And from P to P dash, the displacement by a planet, it is now take as a height. So vector delta r vector. So area is how much? Delta A vector is equals to 1 by 2 of vector r cross delta vector r. Now we will divide both sides by delta t with respect to time. So vector A by delta t is equals to how much? 1 upon 2 vector r. Now vector r is a constant term because the radius of the planet, radius of the elliptical orbit in which the planet is moving, and the distance, or you can say the distance of the sun and the planet, is constant. So here delta vector r means the displacement by the planet with respect to time. So delta r vector by delta t. Now we take, suppose that in a very short time interval or at any instant of time, that is delta t tending to 0, we have dA vector over dt is equals to 1 by 2 vector r cross dr over dt. Clear? Now what happened? 1 by 2 vector r dr over dt is nothing but displacement by time. Here you can see this is your displacement by time. And what is the displacement by time? Is that it is called as velocity. So we will replace here dr over dt as vector v. I hope you understand it. So finally, here you can see that we multiply and divide it by both sides m and m. Here you can see we multiply 2 by m and also v by m, v into m and 2 into m. So we multiply and divide it both. But as we all know, vector r into m, v is equals to j vector, means it is an angular momentum. So this is nothing but total angular momentum, your vector r cross mv. This is your angular momentum. Here it is written that, but vector r cross vector mv is equals to j vector, the angular momentum of the planet with respect to the sun. So after all, here you can see dA vector over dt is equals to how much? 1 by 2m, and we replace this term by vector j because it is equals to the angular momentum of the body. Since vector j is constant, so the aerial velocity, that is dA vector by dt, is also a constant. This is the Kepler's second law. Why it is constant? Because it is totally dependent upon the angular momentum here. Because the mass of the body is constant, so the dA vector or aerial velocity is totally dependent on angular momentum. Now we come to Kepler's third law. This is your Kepler third law. Kepler third law can be readily proved by assuming that the orbit of the planet is a circle of radius r. Now they replace firstly they say the planet moving around an elliptical orbit. Now they are considering that the planet moving around a circle whose radius is small r with sun, and sun is at the center. This is your Kepler's third law. The sun gravitational attraction provides the necessary centripetal force to the planet to orbit around the sun. As I already told you that the gravitation force imposed by the sun over the planet is provided the necessary centripetal force to the planet to move around its orbit. So here we take gms into m by r square equals to mv square upon r. Clear? Now what is capital G? Capital G is nothing but the gravitation constant. Ms is the mass of sun, small m is the mass of the planet, and r square is the distance between the sun and the planet. So this is the gravitation force of attraction by the sun over the planet. So it is equals to how much? It is equals to the, where is mv square upon r? This is the centripetal force. As I already told you that the necessary centripetal force is provided by the gravitation force of attraction which is imposes by the sun over the planet. I hope you understand it. So from here you can see the m and m is cancel out because in both sides, in left hand side and right hand side, both are m. So we cancel it. So finally we get gms by r square is equals to how much? V square by r, where ms is the mass of the sun, v is the orbital speed of the planet. Clear? Orbital speed means with how मतलब कितनी स्पीड से the planet is moving around its orbit. अपनी orbit में planet जिस स्पीड से मूव कर रहा है, that is known as orbital speed. The planet complete one round of the orbit in a time period which is given by how much distance it will cover. If a planet moving around a orbit, then it will cover total circumference of the circle which is your 2 pi r. So v is equals to 2 pi r by t. As you all know, speed is equals v is equals to 2 pi r, total circumference divided by time period. I hope you understand. Now we substitute this value of v, velocity, in the above equation we have find. Here you can see we put this value of v square in this equation, which is your equation number 1. So when we put this value, we get gms by r square equals to how much? In place of v, if 2 pi r square the 2 pi r, then we will get 4 pi r square into r square and t square by r. So after solving, we will get the time period is equals to this. This is the time period, 4 pi r square gms into r cube. So as you all know that 4 is a constant term, pi is also a constant term, g is a gravitation constant, and mass of the sun is already a constant. So the t square or time period, square of time period, is totally dependent on the distance, that is your r. So we can write it like this: t square equals to k times of r cube, or you can simply take it like t square is proportional to how much? R cube. Clear? This is the third law of Kepler. The constant k is same for all planet and has a value. How much the value of constant? This is the value of constant, which is your 2.97 into 10 to the power minus 19 second square meters per meter square. If the orbit is an ellipse, then r may be replaced by semi-major axis A of the ellipse. As we all know, the ellipse has a major and the minor axis. So that's all for the today's class.